And unlike the webinar that I did on Tuesday, this one's being transmitted out of our office in Southern California in Irvine. And this is part of our Hazop facilitation webinar series, and our objectives are to share a lot of our insights with what we consider some of our core competencies in our engineering consulting support, which is providing Hazop study and LOPA facilitation support. This webinar is an ongoing series trying to share those insights. We've gone over a lot of details. I'll share with you what we've done in the past. You can access the previous modules off of our website. But before we get started, let me talk to you a little bit about logistics. The mechanism for this webinar and this broadcast is using a WebEx interface, which does provide complete two-way communications. In fact, we do a lot of, not a lot, but we get involved in a fair number of Hazop studies, long distance, where we can just pull up the WebEx interface and just run with it and really pull a team together very quickly. All that said, it does provide two-way communications. However, because you as a participant may be having other meetings, phone calls, shuffling of papers, etc., everybody's on mute until such time as we get to the question and answer period, which will be at the end of the presentation and actually at the end of the interactive workshop, which is a little difficult to do via webinar, but you'll get the hang of it in just a little bit here. If you do have any technical problems, you're welcome to call the number on the screen, or if you want to call directly to our local office here, it's 949-282-0123. That's 949-282-0123. Also, if you've got a video image in the upper right-hand corner of your screen, which I hope you do, you're welcome to grab the side of that window and adjust the size to your heart's content to make sure it's comfortable for your viewing. Some people want to see more of me, some people want to see less. Feel free to go ahead and make it as comfortable as possible for yourself. You should also be seeing on the left-hand side copies of the actual presentation. I'm anticipating probably about 45 minutes to an hour this morning to run through the materials and also interact with you guys a little bit long distance and share some key concepts with respect to industrial heater, industrial furnace, burner systems. I think that's it for logistics. What we're trying to accomplish today, there's a lot of insights for what we've done in the past with respect to the evaluation using Hazop, LOPA techniques, other PHA techniques, as well as quantitative risk assessment on industrial heater designs and burner systems, and a lot of the fairly advanced protection systems designed to keep these devices safe. We want to share with you some of those insights, put it in the framework, in the context of a Hazop, use simplified LOPA data to show the trends over time in terms of the progression of improvements with respect to the safety shutdown features. And we want to look at some of the new and current design features and share with you some of the good and bad parts of that. We're also, not only are we doing part of our Hazop facilitation series, but we're also presenting this in the poster session at the Global Congress on Process Safety next week in Chicago. This gives us a little opportunity for a dry run and fine-tuning, and your feedback is appreciated, either during the session or afterwards. So let's go ahead and get started. Again, well, I guess we'll get started faster if I get the little tool here on. My name, again, is Steve Maher, and I'm one of the engineers on staff here at Risk Management Professionals. A lot of my background over the years has been associated with doing Hazop studies and applying quantitative risk techniques in a variety of different contexts, including LOPA. And I want to share with you some of those insights. And there'll be time for interaction. If you have other insights that you'd like to bring to the table, share with the team. You're welcome to either ask to be brought into the audio mode at the end of the presentation so you can join in an interactive discussion, or you're welcome to pose questions via the chat window on your screen. Those questions go to our producer, Solveig Sather. She'll digest those, reiterate those to me, and I'll make sure that I share either those insights or questions and hopefully some answers with the group. So let's talk about what we've done in the past. In previous modules, we've looked at the history of PHA techniques, process safety management, and risk management programs. How do you find the optimal approach for the project that you're working on? It really makes a difference. Are you in the design phase, or are you operating a facility? If you're in the design phase, is it the feed stage of the project, or are you in detailed design? Where you're at, what you're trying to accomplish, makes a big difference in terms of the kind of techniques that you choose. Something else that's not part of our Hazop facilitation series is another oral presentation we're doing at the Global Congress on Process Safety next week, is on inherently safer designs. And a lot of those issues in terms of how to apply these techniques and address ISD issues are things that are very important to consider if you're trying to lead a team to look for potential weaknesses in the design. And if you're interested in that, that was a webinar that we did give on March 1st. That's available on our website. And if you have any troubles finding any of these things, as always, give us a call. So where you're at in the design cycle makes a big difference in terms of the techniques that you pick. We went through all those in a previous Hazop study facilitation module. How do you maximize the study usefulness and tips on how to maximize quality. A little bit about consequence analysis, because it's important to understand the phenomenology, what's happening when you decide on Hazop study scenarios. Preparing, that's really appropriate. And in fact, one of the nice spin-offs for us doing these modules is I was in Houston last week speaking with a client to get prepped for starting on a Hazop study for their project. And when they were asking questions like, what do we need to do to get ready, I basically just gave them a link to our webinar module, and it lays out all the things that you need to get ready for the Hazop study. Causes and common mode failures, we've also looked at unusual operating modes. How do you define useful safeguards? And we also touched upon things like common mode failures during that module, and we'll be talking more about that this morning with some specifics on industrial heaters. Done some workshops, facilitation techniques, and also quantitative techniques. And one of the special things I think we did in our last module was looking at what I consider a real bugaboo in the mindset paradigm for when people are looking at these Hazop studies. A lot of people bring in this concept that they refer to as double jeopardy, which usually is used in an inappropriate context. And that module really goes into when's the right time to consider that and when isn't. So what we're going to cover today is looking at the evolution of heater and heater burner designs, looking at the design bases, current design standards, how design standards, analysis, and all these things kind of fit together. Looking at key improvements to heaters and what's happened over the years. Then with some interactive, a little bit on the interactive side with respect to our webinar, I want to look at different vintages of heater burner, show you the progression, and show you how that translates into a lot of the analysis techniques and how this evolution in protection systems has actually had an impact on the overall safety of heaters. So we're going to look at very simple systems, then the evolution introducing pilots, automatic isolation of fuel gas, separating control and protection systems, redundancy and diversity, and then recent additions with the automatic double block and bleed systems that a lot of people are now applying on the pilot gas lines and also their fuel gas lines. And at the very end, I'd like to draw some conclusions, and as always, if you guys have additional insights or things to share, always love to get additional input. No matter, I've been teaching Hazop studies since 1986, and for all those years of doing this, there's always something to learn, new techniques, new ways of doing things, new designs, new approaches to handling things like protection system design or even introducing inherently safer design features. So let's talk again and just remind ourselves what the Hazop study is about. And I'll spend less than 5 minutes on this because you have seen this before. The Hazop study is a form of it's an analysis tool that emulates the big picture. And what's the big picture? Well, if you're trying to find weaknesses in the system or ways to make it safer, you want to understand not just, gosh, is it really bad? Because something can be horribly bad, but be so unlikely as to be impossible and something not worth worrying about. Well, gosh, do you look at things that can happen all the time? Well, things that are unpleasant or cause the operator to scramble to maximize design efficiency happen all the time. Is that a problem? Is that a safety risk? In many cases, no. So it's really understanding the likelihood and the consequences that gives you the big picture and understanding are there weaknesses. The Hazop study is a good fundamental workhorse engine in industry of a PHA technique that allows you to delve into that, lay out the scenario in a form that a team can understand, let them pick it apart, and then you can understand how likely the event is, how bad the consequences are, and are there any weaknesses that you need to address. So the Hazop study is part of this universe of quantitative risk assessment techniques, and understanding what your objectives are and what you're doing with it is of critical importance. As a quick example, here's a high-pressure tank feeding a low-pressure system, and it's on level control. Well, what can go wrong here? Well, a key thing in terms of investigating what can go wrong is to use the deviation matrix for a Hazop study. You combine operational parameters such as flow, temperature, pressure, and level with guide words such as no and more or reverse, and you combine them to look at deviations, no flow, higher level, higher temperatures, to get an to drive you towards what scenarios can lead you to potential problems. Then you cycle through this, ask about the process deviations, potential causes, potential consequences, cycle through it to develop scenarios, and as you're doing that, you risk rank it, get an appreciation for its importance, then you can make a good judgment, usually with the team, in fact it should be with the team, on what's important and are there weaknesses that need to be addressed. So this is a cyclic approach, scenario by scenario. It's meant to be very much a very thorough technique for this kind of evaluation. Here's a quick example that you've seen before of how you document this. It's usually tabular. It's almost always tabular with causes listed, consequences directly associated with the cause, and then safeguards that are the barrier between the causal event and the consequences. How do you handle common mode effects? Again, the safeguards column, you'll usually document if you've got a transmitter or something that may be common to the causal event, and also the safeguard that you'd like to take credit for. You should be considering that in your evaluation of the risk ranking and the overall importance of the scenario. When you're doing that, if the team understands and can keep up with you and you can document it simply like this, great. If you need to take it and make it into a separate scenario, we talked about that, use that. It's a powerful way to get people's attention on really key issues. And if you're the engineering contractor coming in as a facilitator, like many of us do when we're helping clients with the job, you want to make sure they clearly understand it, and you want to make sure it's clearly documented so somebody can pick up that document later and really work back from the team's conclusions. Did they really understand, are there common mode failures or common transmitters? So that's where you're trying to go from that overall, what's our objective with respect to looking for weaknesses from a simplified P&ID, which illustrates the function of the process, and translate that into something that looks at weaknesses. That's the overall framework for the Hazop study. So what I'd like to do is now shift gears, and this is the main theme of this little presentation that we're doing next week at the Global Congress on Process Safety, and that's looking at heater and heater burner designs and looking at that evolution and how does all this tie together, and how do you use techniques such as Hazop study and LOPA to really get an appreciation for are there weaknesses that need to be addressed. This may seem almost comical to you, but industrial heaters have been around for a long time. In the lower left-hand side of your screen is an example of an early form of heater. Steam boiler systems, often manually fed with coal, logs, whatever it takes to make a fire, heat water, minimal controls, very simple design. Also, way before regulations and standards, very prone to failure. A lot of people were hurt and killed. Leading to the right, you've got modern industrial heater systems, many applications in refineries and heavy industry and chemical processing facilities that have a lot of years of experience, design guidelines behind them, and some very advanced control and protection systems. And that's the overall framework that I'd like you to think about, is that kind of evolution. Early heater designs, as I mentioned, had very simple control systems. You're looking at one in the upper right-hand corner. Manual control at its finest. It's great as long as the guy is experienced, paying a lot of attention to where you put the coal, evening out the heat distribution on the coal grid and the whole bit, so you get what you need out of the actual boiler. Very simple design, obviously very prone to human error and having problems, and obviously a lot of people got hurt. There's a little schematic on the lower right-hand corner also showing that. So early heater designs had minimal controls, very minimal safety features. A lot of times they would gag a relief valve if the noise or they were losing steam and they wanted it to power the locomotive, obviously causing accidents. A lot of things that over the years people wanted to work out from that. And what drove those improvements? Well, you know, when you hurt somebody, that's bad. When you blow something else up that's costly. So really a lot in terms of market forces drove that, along with designs and guidelines, brought us to where we are today. So what are the design bases for heaters? Even in the absence of regulatory requirements, basically market forces drive this. Heating efficiency, trying to minimize nuisance shutdowns, and also trying to optimize safety margins. These are things that drive you towards design improvements, both in the efficiency and operation of the heater, and also with respect to safety. And along with that, in parallel, design standards evolve. You'll recognize most of these that have various bits and pieces from the control and protection design to the metallurgy and types of processes that you can use on these industrial heaters. So realistically, there's a parallel evolution of market forces that drove this towards more sophisticated technologies, the need for more sophistication in heater design, and along with that came standards. So the design, how you operate it, the analysis, all keep pace with guidelines and standards and the regulatory requirements, and they're all cyclic. As you keep pushing the limits on heaters to get them more efficient, as you're using new process materials that are looking at temperatures and pressures and chemicals that require you to use exotic metallurgies and things, all those work together towards driving the technology and the level of sophistications and some of the things that we've seen today. This graph shows is a good look, gives you a little bit of background on what's happened as the design of these heaters has evolved. Basically, the objective has been to increase availability. Well, over time, too, you want to decrease risk, but along with those decreases in risks, you've also got to decrease your nuisance trips. If you just put so many safety features on the heater such that it's constantly shutting down, people are just going to disable those. And instead of actual safety improvements, you've just got a big mess on your hand where people think that there's some safety devices and protection features, and there's really not. So the evolution of heater designs has to address availability improvements, make sure heaters do what they want, do what they're designed to do, decrease nuisance, decrease risk, and keeping pace with that decreased risk has to be decreases in nuisance trips. And a lot of what's happened in the past 2 decades with respect to the evolution of control and protection features and the introduction of microprocessors, fault-tolerant sensors, voting logic, and things that are built into these devices have really worked together towards that goal of improving safety, decreasing risk, and at the same time minimizing the potential for nuisance trips. So that's what we've seen with respect to heater design over the past decades, how they've accomplished it through these various applications of control and protection systems. And would you make a note that I'd like to include in the CCPS presentation the overall timeline of the different types of control and protection systems with those bubbles that I've used before? That'd be really cool. So what I'd like to do is start working with you to look at some of these systems and how does that translate into Hazop studies and other different burner designs. So I'd like to start with a simple burner system design. This is a heater. It's got a radiant and convection section. I'll just start in the upper left-hand corner. Basically, you've got a feed coming in. It's on flow control. You got a fail-open flow control valve for reasons that either will become obvious during the session or you already know about. You've got a manual bypass. It gets split into two passes, and as it goes through the heater and then comes out, and its outlet temperature is measured, and that's used to regulate fuel gas supply, and you're coming out with a hotter process material than what goes into the heater. The temperature transmitter on the outlet feeds a signal to a controller that feeds air to a diaphragm on a temperature control valve that's modulating the flow of fuel gas into the heater. Very simple, very basic design. Some of the earlier designs, a lot of them didn't even have a pressure control valve that's illustrated here in the lower right-hand corner, PCV-1, to modulate the pressure or step it down to a constant amount that allows the control valve to regulate a little bit easier. A lot of them just had the simple control valve. Now, this is a very simple design. A lot of the early heaters also didn't have separate pressure control on your pilot gas, which is the line at the bottom that goes into the heater. They just had a manual throttling valve that controlled the pilots, and once they were stabilized, basically kept at that same level. A lot of good and bad things associated with that we'll get into. For things like this, you basically had some basic process alarms, low flow alarms that would go off if you had low process flow for reasons we'll talk about in a second. high process temperature, and also flame outs were introduced in the 80s, that if there was a flame out of in the firebox, that would at least generate an alarm and get the operator's attention to want to do something. So this is a very simple design where you've got flow control in the process, temperature control in the fuel gas, a constant pilot, and pretty robust overall. But let's take a look at what sort of things that can go wrong. So let's start applying some of our knowledge of Hazop study techniques and think about what's the first thing that you do when you get into a Hazop study or you're facilitating it. First thing you do is ask what sort of things can go wrong. What are the major consequences and issues that you want to look at here? Well, one of the things that you want to look at for a heater in general, you're concerned about excess process temperatures that can exceed design limits on tube metallurgy. You might be concerned with rich mixtures in the firebox that can lead to potential explosion hazards or other types of damage, or even pressure pulses that can cause damage. You might be concerned about a flame out that results in this buildup of gases, and after it builds up and you don't have a flame and it finds a hot spot on the heater or some other ignition source that flashes back to the heater, can cause serious damage or perhaps even injury. What kind of consequences do those lead to? Well, all those lead to equipment damage, and in many cases burning down a heater, which is very embarrassing and very expensive, but in a lot of cases that doesn't directly cause injury. The flameouts, buildup of unburned hydrocarbons in the fireboxes have blown up a lot of heaters and resulted in a lot of injuries over the years, and those are a lot of the key things that people look at. So we're going to look at a couple of these key consequences and the causes behind that and think about the scenarios associated with that. Okay, so this is not on your handouts. This will be passed out later, but this is a summary of what we just discussed of key consequences that you want to think about when you're looking at a heater. There's rich mixtures in the firebox, excess firing. We talked about potential tube damage. Flame impingement can occur under cases where you've got either forced or natural draft conditions and significant amounts of excess fuel gas. Tube fouling. If you have excess firing, buildup of carbon deposits on tubes or some other means of fouling, it can generate hot spots that lead to tube failure and release of the process materials into the firebox. Now, what are the process materials? If you're talking about flammable materials, it can feed the fire, burn down your heater, or cause some other significant problems. If you're talking about toxic materials, it can result in toxic materials coming out the stack and going in places where you weren't expecting them to, and maybe some potential for serious injury. We talked about loss of process flow that could lead to tube failure. Contaminants in the fuel gas supply can also cause problems with heaters, and we also talked about flameouts. So what kind of causes are associated with that? All of you have in front of you a copy of that simple burner design with the flow control on the inlet, the temperature control on fuel gas, and also the pilots. So what sort of things do you need to look at there? What kind of causes do we need to look at? Well, you use your Hazop deviation matrix to basically look at no flow issues. So you look at no flow of the process. Now, when you characterize that during a Hazop study, you might look at that flow control valve malfunctioning closed, or one of the block valves on either side being inadvertently closed. It's okay to document them like that, along with any sort of instrumentation feeds that go into that, like that flow transmitter at the inlet. Documenting that as one sort of thing that leads to loss of flow is a fair cause, and that's one of the things you'd want to look at. What about the other no-flow cases? No flow of fuel gas? Well, a lot of times it's really not a problem if you get a complete shutoff or if you really lost complete flow. Well, what if you've got a decrease in fuel gas? What if it goes down to the point where you don't have quite enough to sustain the flame, but you can still feed gas? So your flame goes out and you may still have gas going into your heater, and the pilot is a critical barrier or a safeguard towards helping prevent the buildup of unburned hydrocarbons and an explosion in the heater firebox. You might also look at no flow of pilots, but if it's already covered as one of your safeguards, you don't need to do that as a separate item. With respect to more flow conditions, that's another Hazop deviation to do. You'd pre-populate your Hazop study with maybe excess flow from the process, which usually is just an efficiency issue. And another one might be excess flow of fuel gas. Maybe that temperature control valve malfunctions open, or the bypass opens up, or that temperature transmitter fails low such that it tells the control system, I want more fuel gas, let's open up that temperature control valve. So these are the kind of things that you'd want to look at with respect to causal events during the Hazop study. And I've taken the liberty on the next slide, which will be passed out and sent to you after this module, of key causes that you'd want to look at. Now, I took the liberty of abbreviating them for our presentation. When you document a Hazop study, we have talked about documentation in previous modules. You'll want to spend a lot of time elaborating that, looking at failure modes, and making sure it's crystal clear, and prolific use of tag numbering to make sure that all the information is there and it can be deciphered later. Here we're talking about the flow control valve malfunction closed or failing open, the pressure control valve that's supplying fuel and pilot gas failing closed or failing open. It's just a self-regulating valve, so that's how you document it. The temperature control valve failing closed, and the pressure control valve failing closed. All those things are key causes to consider, as well as tube ruptures. Maybe you've got inappropriate metallurgy, and over time, it's just going to become damaged. I've also done Hazop studies where I've seen tube pressure ratings below the actual operating pressure that they're operating the heater at. Over time, they switched out a heater to another service, and they started charging it with more pressure than it was originally designed for. Nobody had bothered to take a look at that or implement management change appropriately. So looking at tube rupture, talking about tube metallurgy, various design conditions, very important. Also the stack damper. A lot of the more modern heaters where you're really trying to economize the operation will have various forced or induced draft implemented on the heater. For a lot of the older heaters, even manual control, you still have to look for what if the stack damper is closed or fully open, and what does that do to your heater. And even under some conditions, malfunctioning open, mispositioned open, can be a significant impact. Pilots, we talked about that. Pilots should be a key safeguard, and that's the easiest way to document it. There may also be conditions where the pilots need to be treated as a causal event. And also the second one from the bottom, startup conditions. Starting up a heater is one of the most dangerous times to do it. A lot of the modern startup protocols use control systems with interlocks to try to prevent configurations such that you might have a buildup of hydrocarbons, and then you like to light off the heater and cause a significant problem. There's a lot of interlocks that are built into modern designs, but still, regardless of the number of interlocks, you want to make sure you go over the procedures. Do the operators understand them, or do you have some folks who are used to operating heaters a little differently and go in and turn off the interlock system, bypass it, and just start up the way that they're accustomed to, even if it's not documented like that. All these things need to be looked at for the Hazop study. All right, so that looks at a simple burner design, and we're going to get into some quantitative results of how these pull together in just a few minutes. Let's talk about some other features and how they would be treated. The next thing I'd like to look at is another design evolution issue, was basically automatic shutdown of the fuel gas. Well, when do these things come about? They come about in a lot of cases because somebody's had an accident, and the guidelines, regulation standards are being responding to that, in not trying to predict what's going on, but they're in a response mode, and they're not really doing anything other than reacting to the problem. But one of the first things, the early designs did not have a lot of these shutdown features because they wanted to maintain heater operation, maintain the process at all costs. And after accidents and after guidelines and standards came about that called for this, they started looking into automatic shutdown features on fuel gas. Well, some of the early ones and very simple ones were a simple interlock like you see in the center bottom of your screen for TCV1, TCV being the temperature control valve that's feeding fuel gas into the firebox. And basically, it's just a simple solenoid where the instrument air that powers the valve goes through the solenoid, and basically the solenoid opens and you dump instrument air and you close the valve. It's a fail close valve, so when you lose instrument air, it closes off. So that was one of the early design additions that allowed for some sort of automatic shutdown. Now, what was the solenoid tied to? It's not drawn here, but in the upper right-hand corner under characteristics, as well as the various alarms associated with flow, temperature, and flame out conditions. As they had these automatic shutdown features, they'd have a low-low condition on flow, a high-high condition on temperature, or a low condition on your flame, or basically a flame out condition that would trigger opening of the solenoid, dumping of the air, and closing of that temperature control valve. So how do you address that during a Hazop study? Obviously, there's some common mode failures here. If you're pulling the signal from the same transmitters, the transmitter can be a common mode failure. And also realize, even though it's an independent shutoff, you're dealing with the same valve, the same end device, where if that end device has a problem, or if part of what's causing this accident is that you're putting the heater on lower duty and you're telling the temperature control valve to throttle back, or it's trying to do it automatically, and the valve sticks. And the valve doesn't throttle back, and you keep feeding the same amount of fuel gas into the heater. Well, under low process flow conditions, or even flow stagnation conditions, having that same amount of heat input into the firebox can result in heat up of the skins on the tubing and potential for failure. So you've got to look at, again, the Hazop study looks at all these different operating modes, and when you're documenting this, if you're putting this as a safeguard in the Hazop study tables, you need to make sure that it's very clearly indicated that there's a potential for common mode failure. Other innovations that were introduced was that people were looking at the supply of fuel gas, potential for contaminants, and introducing knockout pots, along with various level control alarms if there was a buildup of liquid. Sometimes they'd actually have a level control valve that would drain the knockout pot. A lot of times, if there wasn't a lot of contaminants in the fuel gas, it would be manually drained, and there's a whole host of potential problems with that you'd want to pick up during your Hazop study that we'll not address today. Another key innovation that people started introducing was getting pilots off of the same supply as the fuel gas. A lot of good reasons for that. If the fuel gas is interrupted, or you get a bump in the fuel gas and you get a flame out because there's been a bump, you might lose your pilots too. So you might lose both your main protection feature at the time that you really need it. Also, if contaminants get in there and you've got these pilots continuously running, a lot of times the orifices are sized such that these contaminants can build up around the orifice in the combustion zone, and as they build up, eventually it can build up and build up and build up and plug, and then you've got no pilot, no key protection feature for conditions such as a flame out. So taking it off of a conditioned natural gas line, often city gas, into a facility was another key innovation. Again, as you're documenting all these in the Hazop study, they go right into the safeguards table. There's room there. Do more than just document it. If there's common mode failures or if there's potential problems, go ahead and make sure you make note of that. And I'll show you how that pulls together quantitatively in just a couple minutes. Okay, next. Okay, separation of control and protection systems. As I mentioned before, end devices using the same transmitter, over time, people realized that valves can stick, transmitters can fail. Gosh, you talk to a lot of folks back in the 80s and 90s about what could go wrong here, and you say, what about the temperature transmitter? Oh, that never fails. It always reads just fine. And gosh, they maintain it annually. Well, what did they do annually? Did they do a functional check? If you're only operating one heater for a year or two, you really haven't had enough length of time or a statistically significant population of heaters to really draw any conclusions about the reliability of the transmitter in the first place. So there's a lot of false sense of security for these transmitters and some of the early devices that came out. People realized over time that they really needed to move towards a separation of control and protection. That's depicted very simply here with the temperature control valve number 1. Upstream of that, there's a separate isolation valve, XV-3, that's a fail-closed valve, and it's held open by instrument air, and if the solenoid is de-energized and trips and vents the air, the XV-3 will close. Having separate signals, separate transmitters, and also a separate end device meant that you took out a lot of those common mode failures, reduced the potential for one problem to cause the event, and disable your key protection features. Here your control device is still TCV-1, and your protection feature is XV-3. It's separate, and it provides a very significant improvement in the overall reliability of your protection features. Let's take a look at one more design feature, and then let's take a look at what that's doing to overall reliability. And I just went too far forward. It's this one, the one that says fault tolerant and voting logic. Good, we're synchronized. Over the years, although they had a separate shutoff valve, a lot of people realized, well, gosh, we don't just necessarily need to shut off fuel gas. If there's a continuous leakage of pilot gas, and if the pilots aren't lit properly, you can still, albeit slower, build up unburned hydrocarbons in the firebox and have the same problem with a rich mixture in the firebox, no combustion taking place, and if this rich mixture in the combustion zone gets into an area where it can find an ignition source or a hot spot, you can touch off a significant problem. You can touch off a significant overpressure event in a heater, and if you've seen a heater that's had that happen, you'll notice the sides have basically blown off, and if you're lucky, the superstructure is still there, and there is nobody nearby to get hurt. So what they realized is that you need to have positive shutoff of pilots. They took a good look at this, and some of the current standards have settled on an automatic double block and bleed function, one for the fuel gas that you'll see on your left, XV1A, B, that isolate, and 1C that opens to vent just in case A or B don't work properly. In the pilot, on the line for the pilots, the same thing, but for shutdown and protection loop 2, normally A and B are 2A and 2B are open, and you're flowing pilot gas to the pilots. 2C is closed. In the event that you want to have positive isolation of your pilots, 2A and 2B should close and 2C should open. So there's a lot going on there, but when you look at the use of tight shutoff valves, when you look at reliable features, and what's not shown here is the protection logic, that's depicted in the upper right-hand corner in the box as for the previous slides. You can apply voting logic as electronics get less and less expensive, and these get more and more applied. The transmitters become more reliable. The voting, you get more that can be installed from a cost-effective perspective, and you can use those different signals and voting logic to feed that back and have truly very independent protection features with highly reliable signals. So people have realized over the time, and unfortunately it's taken time, it's taken people's lives in many cases, and a lot of damage for people to come to this conclusion, but they realized that separating control and protection makes sense, having independent shutoffs makes sense, and in a lot of cases, especially as digital electronics become more available, fault-tolerant systems, etc., having multiple transmitters feeding voting logic system allows you to achieve, remember those curves earlier, the levels of low nuisance shutdowns and also low risk together and accomplish those objectives. So there's been a lot of back and forth and a lot of painful evolution, but that's where people have gone to. And I guess what I'd like to do next is show you a way to look at that from a Hazop and reliability perspective to kind of not only show how some of this evolution can be shortcutted, but also I'd like to illustrate some key concepts that I'd like to see you using when you facilitate Hazop studies. But right before we get into that, some of the other advanced features that we're not going to get into today are forced draft, induced draft systems, automatic damper controls, sensor diversity, and also some of the emergency response features such as snuffing steam. So a lot of numbers on the screen. Let me hold your hand through this a little bit, and it's not as painful as it looks, and we'll kind of get through this. On the left-hand side, we're looking at different configurations of a heater design. We looked at a very simple one, simple temperature control valve. Configuration number 2 was automatic isolation of the valve by dumping the air to the valve. Number 3 is separating control and protection systems. And number 4 is the introduction of reliability and redundancy voting logic for a lot of the modern systems. Let's first look at loss of process flow that can cause flow stagnation or under low flow events, excess firing, and tube failure. Well, as we talked about before, that could be an initiating event such as FCV-1, malfunctioning closed, or a block valve inadvertently closed, or possibly driven by the flow transmitter. Keep that in mind. Well, for the early burner designs, what's the key protection feature? It's a low flow alarm. And that low flow alarm is good except for one thing. You've got a potential for the flow transmitter that can actually fail high and say, gosh, I want to throttle back on that flow control valve. So let's go ahead and take a look at that flow transmitter. And if it does do that, you've also disabled your alarm. So in a condition where the flow alarm works, using some simple values that are used commonly for LOPA, you might get a factor of 10 improvement in safety, and basically your protection system have a 9 in 10 chances of working or 1 in 10 chance of failure. All these are looking at unavailabilities to simplify the arithmetic and take a look at that. I put in the brackets there CM because whether you factor it into the numbers, which to really do that properly, you'd use fault tree and quantitative risk assessment, or you denote it by, in your safeguards column, spelling out whether it's common mode failure. You want to make sure your team understands that, understands the potential for a transmitter failure that can initiate the event and defeat your key safeguard. Now let's go a step further and make sure, because a lot of you are going to be going like, wow, we shouldn't consider that for LOPA. And you're absolutely right. If you're doing a LOPA calculation, even though we're using numbers here as representative figures, the rules of LOPA means that you would typically not list that as an independent protection layer. But for our purposes, I'd like to show you how that evolution of safety system has had a very positive impact on the overall decrease in unavailability of your protection systems. So for that same event, let's take a look at design configuration number 2. If you've installed an automatic shutdown feature, that's the FALL that initiates the dump of the solenoid and closure of the temperature control valve, that usually adds another decade of improvement. But keep in mind that if you're using the same flow transmitter to feed all these, that same flow transmitter can defeat if it fails, it can cause your valve to close, cause the low flow alarm not to work, and also if you're feeding the shutdown function, that shutdown function is not going to work either. So again, I'm putting numbers there as indicators of improvements. Under a lot of cases where you're not looking at the flow transmitter failure, you would get that low flow shutdown actually helping you. The fact is you need to indicate either in the Hazop study, very, very important, that there's a potential for common mode failures, and consider that when you're looking at are there weaknesses in the system. The reason why I emphasize this may sound, because you've been through the previous Hazop study modules, like, well, gosh, doesn't everybody do that? Well, they do that if they've learned properly, but I don't know how many times I am given a Hazop study from somebody else who may not have been careful documenting this or guiding the team, where they've taken credit for all these things, and there's nowhere indicated that anybody's thought of the potential for these systems not working properly because there may be common mode failures for something else. Let's look at configuration 3. As designs evolved, people started separating control and protection. Well, gosh, what does that do to your overall protection system reliability? Your flow alarm, if you're still taking off the same transmitter, still has potential for common mode. But if you have an independent shutdown, and with an independent device and an independent solenoid, your FALL or low flow shutdown actually gives you the credit that you want, so you do get a net improvement in protection system reliability. Taking a step further, for the modern designs, reliability and redundancy, that include reliability and redundancy, and all these modern voting logics, and this other device that I put there, an FAX, I'll tell you about that in a second, all these things rolled in really provide a lot of additional robust improvements towards overall protection system reliability. The first one is if you really got multiple transmitters, you're no longer dependent on just a single transmitter failing that can defeat your control and defeat your alarm. For your question should be, well, what if you've got multiple transmitters that are feeding control and the alarm? Well, when you've got multiple transmitters into the signal processing logic, usually they build a discrepancy alarm. That's often characterized as an FAX, X being like a discrepancy alarm. It's the system saying, hey, I've got three transmitter inputs. 2 of them are showing a certain value. One's way off. Somebody needs to look at this. Bang, bang, bang. Let's generate an alarm. So whether you're actually getting a low flow alarm or you're getting that discrepancy alarm, it is truly independent from your control system. You've got one or the other, so you've got one mechanism for picking that up. The low flow shutdown, it's off. It's through voting logic. It is independent. So you really get the kind of improvement that you like, and because you're using voting logic and multiple transmitters, you can really get more improvement than you could for the earlier designs. And for this one, we gave it something equivalent to a SIL2 value, which, so you've seen this in previous modules. The SIL2 would typically be characterized with a 0.01 per demand type unreliability, or very low unreliability. Well, together those give you a net protection system reliability for these functions. There may be other functions, keep in mind, for a Hazop, but for these functions that we're looking at of a net improvement of a 0.001 per demand, or 999 times out of 1,000, you'd expect it to work properly. So what I've done in this column is try to illustrate some of the tangible benefits that you get as these designs have evolved, and I'm hoping you see how that correlates to what you do for LOPA, and that what to look out for with respect to other designs, especially if you pick up or get involved in facilitating an older design for a system. Now, quickly looking at the right-hand column, the same kind of thing, and I'll go through this fairly quickly. As you've evolved designs, you may start from a simple burner design with just a flame-out alarm, a flame-out detector that generates an alarm. Again, back in the early days of implementation, the reliability was such they didn't want it to generate a shutdown because it'd be shutting down your heater constantly as the flame rods would get corroded, or something gets plugged, or some lens becomes opaque, and so they just had them generate an alarm. Well, when you start adding all these other improvements, especially independent pilots off a natural gas system that are a key safeguard, and improvements in the flame-out detectors, and also getting them to the point where they can generate shutdowns and then you use voting logic, you can really see significant improvements in unavailability that translate to improvements in reliability, along with significant improvements because you're using voting logic, modern equipment, and fault-tolerant devices in the nuisance shutdown frequencies too. So this slide to me, and I hope this helps you too, ties together the kind of things that we've looked at for different designs, how you document Hazop studies with respect to listing safeguards, being very careful about common mode failures and looking for things that can go wrong with the system, and also how do you handle it with the team. You know, if the team is not wanting to identify the device, that's fine. You just list it, make a note that says, okay, we didn't include this because of potential for common mode failure. If they insist that, oh gosh, that's a wonderful protection feature, we've used it for 10 years, it never fails, go ahead and put it in there, but make sure you note it's got a potential for common mode failure. And when you're risk ranking and driving the team towards identifying weaknesses, make sure they understand how the system is set up and the potential for common mode failures and what really represents truly independent functions and system reliability. All right, that should tie together a lot. I hope that ties together quite a few things. What I'd like to introduce is a special topic such as automatic double block and bleed systems. It's kind of the same concept that was introduced in the 80s with a lot of injuries that have occurred at refineries because people didn't manually double block in. Well, it was commonplace back then to simply isolate with a single valve and call a contractor in and say, okay, go work on this equipment. Well, they leak, they may not have been isolated properly, people get hurt. So they started adopting, for a lot of designs, especially when you're dealing with higher pressure systems, a double block and bleed manual system, so that you close two isolation valves and open up a bleed in the center or a vent in the center, depending on whether you're dealing with liquids or gases, and allow the pressure decrease so you know you've got positive isolation and the system can be worked on safely. So that was a manual device that was introduced into designs a couple of decades ago. Well, recently people felt like, gee, why not do it on an automatic feature on a heater? So that was that complex design that I showed you, complex drawing that I showed you last with respect to those double block and bleeds on the fuel gas supply and also the pilot supply. Let's take a look at those implications. Again, just to kind of run through this, here's an example of the evolution of these independent shutdown features. Configuration A is just a simple single shutdown valve. That's kind of like that third drawing that I showed you earlier. Configuration B is two valves to provide a little more reliability isolation. Configuration C and D are this automatic double block and bleed, which is commonplace in many designs, with one minor difference between C and D. Depending on how the designer set this up, and we'll talk a little bit more about that shortly, they've sized the valve and located the vent either for just safely releasing the volume between the two isolation valves or safely releasing an entire flow case when you got full flow conditions on that vent valve. So I've seen it both ways, and what I want to talk to you about are the implications of those two different configurations. So keep this in mind, and what I like to do is what kind of things can go wrong here? Well, one of the things that we need to do is look at the function. From a safeguards perspective, it's important that these things are isolated. What other sort of things can go wrong with this? Well, a lot of things that over 50% of the time I don't see in the Hazop study, and it's masked because it's a protection feature and a safeguard, is a lot of people don't consider what happens if that automatic vent valve opens up. When would be a bad time for that? Well, during normal operation, if that vent valve opens up, you could have a lot of gas coming out of that because the fuel gas system is pressurized. During shutdown conditions, if that valve is open and if the valve opens up as it should, and one of those manual valves doesn't close when it's supposed to close, you can still have full flow conditions going out that vent valve. About 50% of the time, I do not see those scenarios in Hazop studies that I pick up because people don't think about what if my safety feature goes wrong? What if my safety feature doesn't work as it's designed to? So let's talk about that a little bit and use some of the, oh, by the way, you'll see this in the printout that you get as a follow-up to this training module of the kind of failures you need to consider. And I'd like you to make sure you think about these things during your Hazop studies if you're facilitating with this kind of configuration. Bullet number 3 is what I was talking about, where you've got the automatic bleed valve failing open during normal operation, single failure. Or another way to accomplish that same flow is if the block valve fails to isolate on demand with the block valve that's in the main flow path with the vent valve open. And basically, it's two separate conditions. The first portion of this condition is a single failure. The second portion is a double failure. And we're going to focus on the single failure. They tend to be a little bit more important. So let's look at how that translates to numerics and some of the concepts that we've picked up using Hazop studies, defining safeguards and common mode failures clearly, and also, even though you can get into a lot more detail quantitatively, I wanted to use simple values that are used in LOPA to illustrate what you need to look for and consider. I'm not saying that every design is different. Every Hazop study, every installation at a plant site is different, but certain things should be considered. Well, configuration A was the single isolation valve. Very simple. That single isolation valve adds another decade of reliability or decreases unreliability by a factor of 10. So you get a 0.1 per demand improvement on that. And if you're looking at, and there's a little footnote at the bottom in what our assumptions are, if we're assuming that you've got a flame out challenge of 1 per year, and between pilots and alarms, you get a 0.1 per demand protection on that, then basically you're looking at a 0.1 demand of a flame out condition where you need this protection, this isolation of fuel gas to work properly. And so that's where you get the net heater explosion frequency of 0.01 per year. Let's look at configuration B. Configuration B is the two independent isolation valves. Well, if each one gives you 0.1 per demand of protection, but they are two isolation valves. They may be maintained by the same person. They may have some common signal processing. You need to look at that. So there's some potential for common mode failure there. Not saying it's significant, depends on the design, but you want to at least consider that. Plus there's another failure mode, and this is why they added that vent valve, is there's a potential for these valves to leak. If the valves leak, and what I did is pulled out, instead of 0.1 per demand of not closing properly, basically 0.2 per demand of having some leakage after closure. So 0.2 per demand is the leakage frequency that I've chosen to be representative, again, to illustrate the concept. If these numbers are all that critical to what you're looking at, you really need to go through and get plant-specific and detailed failure rate data from places like ARETA or the CCPS guidebooks. If you look at leakage of 0.2 per demand, basically you multiply the 0.2 by 0.2 times the 0.1 probability of ignition, because you're only looking at leakage events, you're not looking at full flow. You basically look at the incremental risk posed by leakage of 0.0004 per year. Now, what do those numbers mean? You've really got two ways to have problems here: the leakage of the two valves, or the two valves not working to isolate in the first place. And they really add together. There are two kind of different effects happening here. So that incremental risk associated with leakage is the 0.0004 per year to give you a total risk of 0.0014 per year. What do you do with that? Well, that leakage is why the vents were added. That's the risk that's averted by adding a design where if it vents properly and you prevent that potential for leakage into the firebox, that can build up over a slower amount of time because it is a leak and results in a heater explosion hazard. So configuration C is the vent that has the ability to have full flow conditions, and the vent is located properly such that if you do vent, it doesn't generate a hazard. So for that case, you've still got the two isolation valves, but what you've done is you've removed the potential for leakage into the heater firebox. So you haven't really added any risk, and you've averted that 0.0004 per year risk of heater explosion. That's your averted risk by making that improvement of your vent valve. Now, I don't want to get too much into this, but if you're getting into risk-based decision making and cost-benefit analysis, you can actually look at those values and make decisions about how much you want to spend on this design. But let's look at configuration D, which I have seen actually in the field. Cases where the vent's not routed properly, or it's not sized properly, or it's not designed. In a case like where it can open during normal conditions and you haven't routed the vent such that it can build up a gas cloud, here's a safety feature that really, if you look at just during plant operation, a typical LOPA value, just to represent the kind of failure mode you can get, is 0.1 per year that the valve can open. And if you even take a 0.1 per occurrence of finding an ignition source for that amount that goes through that vent valve, you're looking at an increased potential for fire and explosion and potential injury of 0.01 per year. So you've, instead of averting a risk of 0.0004 per year, you still averted that risk from leakage in the heater firebox, but you've added another risk in another scenario of 0.01 per year, which is a lot bigger. It looks like a factor of about 25 bigger than the risk that you've averted. So instead of improving things in this scenario, when the vent is not routed properly and you can get that leakage, you've greatly increased the risk associated with this addition of a safety feature. And this is not a hypothetical example. These are real examples I've seen more than once. And why does it happen? It happens because the regulatory guidelines that put this forth don't really provide all this background, or the people using it don't really study it. And they put simply on a lot of the P&IDs, when I get them for a Hazop study, it says, in parentheses, route to a safe location for the vent. Well, what does safe location mean? A lot of people are thinking, gosh, the vent only has to release the little amount of material, the amount of fuel gas between the two isolation valves, because that's what it's normally doing. So the design engineer is looking at that and going like, okay, safe location, go ahead and put a 5-foot tailpipe on it and we're good to go. They don't necessarily think about what can go wrong or play the what-if scenario during the design. So it's important to flesh these out, challenge the designer, and make sure they consider those kind of issues. And this slide illustrates exactly why that's the case. And again, I'm saying this because it's not a hypothetical example. This hasn't been considered for a lot of designs that I've Hazoped. And when challenged, the designer, after they realize what's going on, they give oh, we better do something about that, and they fix it. So these are real issues to think about, and it dovetails back into making sure as a facilitator you need to think about common mode failures, you need to think about overall design reliability and protection system reliability, and make sure that it's very clearly documented. Okay, so what kind of things have we looked at? Basically, we have seen the evolution of industrial heaters and burner designs This is giving us dramatic improvements in availability, decreases in risk, and also decreases in nuisance trips. It is feasible. Things have really improved over the past couple of decades. As a facilitator, you need to make sure you carefully consider common mode failures and have to clearly document them and make sure the team understands. When you're to achieve acceptable levels of risk, make sure you apply active safety systems, but recognize they can reach a point of diminishing returns. For those of you who do LOPA, just as you don't want to take credit for multiple alarms if the same operator action takes place as giving you independent protection layers, if you've got additional bells and whistles, alarms, transmitters going into equipment, additional signal processing, but you're still reliant on that one potentially unreliable end device, you really haven't improved things dramatically. And adding all those things or listing them in your safeguards column can mask the fact that there's something else going on here. And in a lot of contemporary applications, you need to look at other safety management systems issues, mechanical integrity, operating procedures. Even recently, with a fairly new design at a local refinery, there was the operators disabled the interlocks during startup because they were more comfortable starting it up manually, blew the heater apart, had an injury, fortunately not serious, but it was very unfortunate and totally unnecessary. Fifth bullet there, automatic double block and bleed, vent location and sizing, extremely critical. I used our Hazop study approach, the LOPA numbers, and our overall understanding of protection system reliability to illustrate that. And also, key thing, when you're introducing new safety features, think about what new hazards can be introduced. Just because it's there to become a safety feature, don't take it for granted that there aren't other things going on. Especially if management of change, you're administering management of change, looking at new things being added, you want to make sure you understand the full impact of that rather than just check the box, oh, it's a safety feature, so it must be an improvement. Think about it. And make sure when you're facilitating that your team thinks about it too. Okay. A couple of things I'd like to mention. Again, thank you for attending. This was one of our modules for our ongoing course on Hazop study facilitation. Again, we consider this one of our core competencies, something we take a lot of pride in doing good quality work on. We use these webinars to train our own persons internally and also to share some of our knowledge to hopefully improve overall application of these things. My career's been going on for some time, and I was actually privileged to be part of the Center for Chemical Process Safety's response back in the mid-'80s, and watching these things improve over the years. And I really like to see a lot of things be shared. I like to see good applications, and I don't like to see the lessons of the past be lost. So I hope you've got something out of this, and I hope you're tuning in on a recurring basis to these. Our next module is going to be how to pull all this together and integrate LOPA, CIS, SIL, and QRA during the overall project. And I guess I'd like to open it up for questions, if anybody has anything that they'd like to address. I guess my question should be, is anybody still tuned in or awake? Oh, anything internally? I'll reiterate it.
All right. You said that the guidelines are moving towards the installation of a vent on a double block of leads. If this can pose additional hazards, why would they do that?
All right. Well, that's a good question. Basically, the question was, design guidelines and standards are moving more towards, and it's becoming pretty much common practice for implementing these automatic double block and bleed functions into your pilot gas and main fuel gas systems. And the question is, why are they doing that if it can pose potential hazards? Well, design guidelines, like a lot of things, and human nature is to be responsive. If you look at the overall evolution of heater designs, and one of the things for those of you who tune into the March 8th webinar that I broadcast out of our Houston project office, you're hopefully enjoyed, but I'm pleased that you tuned in at least to a presentation, an advanced presentation of a paper we're giving and another paper we're giving at the Global Congress on Process Safety associated with the overall evolution of process safety regulations, both for onshore facilities for PSM and RMP, and for offshore facilities, which is the new SIMS program. One of the key things that I got out of that, I was one of the co-authors on the paper, one of the key things that I got out of that was really how responsive human nature is when things go on. If you look at Bhopal, India, if you look at Piper Alpha, even if you look at the Deepwater Horizon accident last year in the Gulf of Mexico and the Macondo well release, the regulations were pretty much responding to that. And that's the same thing for guidelines. Most of the heater designs, guidelines, and standards are really reactive, or they're responding to problems that have occurred in the past where people have been hurt, killed, and the honest truth is, and this is one of the things I really wanted you to get out of this, by looking at reliability numbers, thinking about common mode failures, and really doing your job, and I'm going to go and challenge you right now, doing your job as a facilitator. Part of your job isn't just to sit there and ask questions and let somebody else worry about the answers. You need to guide the team, challenge the team, and make sure they're asking questions on terms of what can go wrong, along with the understanding of what the impact on protection system reliability is. That's, in my opinion, of critical importance to Hazop facilitator, playing an active role in challenging the team, not just a less active or even a passive role in terms of asking questions. And so rather than waiting for the history to tell us the next disaster that we need to design around, use the Hazop study techniques, use LOPA, use your knowledge of all these things, pull it together, because all of these things can be predicted. That design evolution isn't like something that just happened overnight. If you look back at the early designs, and if we apply today's reliability techniques, you could go back and design a lot of the problems out of it. You can evolve things, ask the questions, and keep people from getting hurt. And if I don't do nothing else today, if I can, even if I have to shame prospective Hazop facilitators into asking these kind of questions, I'd like to do so and really challenge you to challenge the team and stay on top of this and move forward with it.
A question from Jose. It seems like a double block valve out of.
Well, that's a good question, and in fact, I'm really glad you asked that for a couple of reasons, because it's a good question, and I forgot to mention the fact that a lot of companies are thinking about this. I mentioned that a lot of times I see where they haven't been thinking about it. A lot of people are. They recognize it can generate a hazard, and in a lot of cases, I've seen where they've removed the vent, they have an internal design standard for only the double block, and they live with that little incremental risk of potential leakage. And a lot of the modern valves that you install for contemporary designs are called TSO valves, or tight shut-off valves. Those valves are designed to have a better shut-off characteristics, less likely to leak. And one could argue that using a TSO valve instead of the vent may be a little bit safer. I haven't gone through those potential calculations. When I see that, and I ask the designer why they do that, if they come back with that answer, I almost feel like applauding, because they've done their job. They haven't just designed it to operate. They've thought about potential failures and designed it so it's less likely to fail. Thanks for the question. That was good. Anything else, Ollie? All right. Well, in that case, I'll wish everybody a good day. And thank you for tuning in. And if you do have any questions, go ahead and call. Right now, my part of my career, I'm just really happy to share information and try to help folks out and keep people moving along the straight and narrow towards operating a safe facility where everybody goes home at the end of the day safe and sound. Thank you, guys. And transition.